Yeah, good morning my dear students. Today I am going to discuss the topic on various background correction techniques used in atomic absorption spectrometry. So in the last class we discussed about the various problems, interferences caused in atomic absorption spectrometry. So how to prevent different interferences in atomic absorption spectrometry using this background correction techniques. So these background correction techniques, basically if you consider these things, the background correction is used to differentiate the sample signal from the absorption, emission and optical scattering of sample from the matrix or from the flame or from the plasma or the graphite furnace, right? The most important for graphite furnace background correction technique is why it is very important in graphite furnace, because they gives the smoke from charring step. So smoke during charring step, pyrolysis or decomposition from heat, definitely this smoke will be a bigger problem over there and that will always cause interference. So to avoid that, we should definitely go for rectifying this background correction as such, right? Now the optical scatter from the smoke. Whenever you are getting the smoke, you will always not have the proper absorption parameter. You will get the unwanted scattering effect also. So the optical scatter from the smoke and the optical absorption by the sample, you have to differentiate both these things. So how you will differentiate both these things? With the help of background correction techniques only, right? So what are all the various correction techniques we are using for background correction in atomic absorption spectrometry? One is beam chopping, second one is deuterium arc method, the third one is Smith-Hayefji method, and the fourth one is Zeeman correction method. What is called beam chopping method? The beam chopping is also called as electrical modulation of hollow cathode lamp in atomic absorption spectrometer. So how will you do this electrical modulation with the help of hollow cathode lamp? Everything depends upon the light source. How you are using in this particular concept in beam chopping for correcting the interferences. It's very simple. Here I have shown here the lamp will be there. There is a rotating chopper. There is a burner. Right? Here the rotating chopper is not blocking the light coming from the lamp. Lamp is what? Hollow cathode lamp. Okay. So what will happen? Whereas in the other case the lamp, and here we are having the burner, that is your flame atomizer or graphite furnace will be there, and between that we are keeping the rotating chopper. So the rotating chopper blocks the light radiation coming from the lamp. Here in the first case the rotating chopper not blocking the light radiation coming from the lamp as such, right? Now as I told you, the electrical modulation of hollow cathode lamp in atomic absorption spectrometer differentiate the signal of the flame from the desired atomic line at specific or same wavelength. Now if you look at this, the light from the lamp is periodically blocked by the rotating chopper. Once we are blocking it with the help of the rotating chopper, so the signal finally reaching the detector is identification from the flame emission. So this is the, whatever the flame emission will be there, that only will be identified. If you are blocking with the help of the rotating chopper or the beam chopper, so the finally whatever the signals you are getting, that is purely coming from the flame emission. Whereas if you are not blocking with the rotating chopper, as in the first case, whatever the signal you are getting, the signal will be mainly due to the flame as well as from the lamp. It is a combination of both the lamp as well as from the flame. Okay. So now what we are doing, if you differentiate, if you make the difference between these two signals, that will give the original analyte signal. Is it clear? So this is how we are making the difference, because I told you already the flame profile, when the flame is coming with outer combustion, so always the flame catches the fire by adding the outside atmospheric air into the flame. So you have to subtract the excess unwanted signal which is causing interference from the flame. So that is the reason we are going for this beam chopping method, right? And very important aspect, beam chopping method corrects the background effect for flame emission but not for scattering. Again, the problem is not solved. It is not useful for scattering effect, only it is an effect for flame emission. To correct the flame emission, we are using the beam chopping method, right? So the second method, whereas the rest of the other techniques like your deuterium arc method, where the other Smith-Hayefji method or the Zeeman effect, these methods are used for correcting the scattering as well as the background absorption. Okay. The first method is purely for correcting the flame emission, whereas the rest of the methods are used for correcting the background absorption as well as scattering effect. So the second method what we are using is deuterium lamp correction. So in deuterium lamp correction, what we are doing, originally the light radiations are coming from the hollow cathode lamp in atomic absorption spectrometer. So what we are doing, we use the hollow cathode lamp. The light will be absorbed by the sample and the light will be absorbed and scattered by the background. If you use the hollow cathode lamp, the light will be absorbed by the sample as well as the light will be absorbed and scattered by the background also. This is the property, right? Now, instead of hollow cathode lamp, I am using some other alternate lamp, a dummy lamp I am using. So, what is the lamp I am using? I am using the deuterium lamp. If I use the deuterium lamp, the light is absorbed and scattered only by the background. Okay, it is not absorbed by the sample, right? So, the light is absorbed and scattered only by the background, right? So, now you can remember that you measure or find out the difference between these two signals. If you find out the difference between these two signals, automatically what will happen? You will get the original sample signal for your absorbance. So, this is a very important aspect as such, right? So, this is all about the deuterium lamp correction, right? Now, coming to the third important aspect, that is called the Smith-Hyabji effect. What is the Smith-Hyabji effect? The Smith-Hyabji effect is based upon the application of electric field, right? So, the hollow cathode lamp is run at high electric current, right? Generally, when you use the low current, when you see, if you plot the wavelength versus intensity, when you use the low electric current, what will happen? You will get the signal for both the sample and the background. Both will be possible. But when you go for applying the high electric current in the lamp, what will happen in the hollow cathode lamp? If you are running at high electric current, what will happen? There is a dip in the central region, right? So this dip is basically, there is an, we can say that the output is broadened. This clearly shows that the output is broadened and dip develops at the central wavelength, which is a result of absorption by the free ground state atoms located between the lamp window and the hot atoms near the cathode. That means it will give only the background. Okay, it will just give only for the background. This is a very important aspect, right? So the absorption by the free ground state atoms located between the lamp window and the hot atoms near the cathode, right? So this is the property we are getting. So what will happen? The high current is the broad background absorption you are getting. When you are applying the low current, you will be getting the sample and the background together. Now you make the difference between these two signals, automatically you will get the original analyte signal, right? Now what is an advantage of this Smith-Hyabji effect? It is more reliable than deuterium lamp correction, but it is less expensive. And the disadvantage is 10 to 75% loss of sensitivity because the analyte absorbs some fraction of light during the high current pulse. When you apply the high current pulse, automatically the sample also absorbs some quantity of the light radiation, right? So that is one of the drawback, and sensitivity will be lost, right? So this is also widely used method. Among all the four methods, this is a used method, very, very important method, Smith-Hyabji method. It is a less expensive method. Now the fourth method is used, which is very widely used for performing the background correction technique, is Zeeman effect. What is called Zeeman effect? The term Zeeman refers to shifting of energy levels of atoms and molecules in the influence of magnetic field. Zeeman is a term which refers to the shifting of energy levels of atoms and molecules in the magnetic field. So it is an excellent expensive technique. How we are using this thing? We are just putting the magnetic field parallel to the light path through the plasma or the furnace. We just apply the magnetic field parallel to the light path in the flame or the furnace, right? The absorption or the emission line split into three components. When you put like that, the absorption or the emission line will be split into three important components, right? So now I can show the example here. I just put the relative wavelength in nanometer, and on the other side I am putting the relative signal on the y-axis. And here there is a zero line, here there is a positive, here there is a negative, right? I am just putting that in this manner. Now what will happen if I put the magnetic field off? I will get the response for both the sample and the background. If there is no magnetic field, I will get only the response for sample as well as the background absorption. But if the field is on, if I apply the magnetic field with a strength of 1.2 Tesla, in that case what will happen? The curve will be coming in this manner. There is a dip in the central region where it is lowered in this side and this side also lowered in this manner, right? That means some of the things will be coming in the positive side, some of the things will be coming in the negative side, and in the center at zero you will be having a dip also, right? So this clearly shows that it will not, when the magnetic field is on, the sample will not give any effect in the magnetic field, only the background will be visible here. Okay, when the magnetic field is switched off, that gives the response for both the sample as well as the background. When the magnetic field is switched on, they will give only response for the background only. So what will happen? You switch on the magnetic field, switch off the magnetic field. So if you alternatively do that, then you can measure the background as well as the sample plus background importantly. So you find out, you just subtract the values obtained for this one and this one, automatically the differences will give the original sample signal. So this is how we are using the Zeeman effect, which is a most expensive technique, but still we are using that. The field off will be sample plus background and the field on will be background alone. So this difference is the original sample signal, right? So example for the Zeeman effect we can easily identify with the help of mercury lamp or the mercury line at 253.7 nanometer. Right? So this is one of the example here. So these are all the various background correction techniques we have used in atomic absorption spectrometry in order to counteract or just rectify the interference problems in atomic absorption spectrometer. I hope you understand in a clear manner. Thank you, my dear students. Thank you very much.